Okay, welcome back everyone. In this video, we're going to cover Unit 1B in the final exam review. So let's just start with number one here. So we want to find the domain of this function. If we're going to find the domain, we have to figure out where this function cannot be equal to 0 on the bottom. The reason we want to do that is because we can't divide by 0. So wherever the denominator here is equal to 0, that's going to give us an issue. So if we look at x squared minus 3x minus 10, and we try to figure out where that can't be equal to 0, it's just like solving this quadratic. We're going to solve it by factoring. We're going to find two numbers that multiply to negative 10 and add up to negative 3. Those two numbers are going to be negative 5 and positive 2, which means that x can't be equal to positive 5, or x cannot be equal to negative 2. And so when we talk about our domain here, we can't have negative 2, we can't have positive 5. Everything else is perfectly fine though, so everywhere from negative infinity to positive infinity, except for negative 2 and 5, is fine. So really the only 2 points that we're excluding are negative 2 and positive 5. And so if we had to put this domain in interval notation, we would say that this is from negative infinity to negative 2, union from negative 2 to positive 5, union from 5 to positive infinity. And so this gives us the domain for this function because, again, we want to find all of the parts of this function, all of the x values that would make us divide by 0 because those can't be included in our domain. Now, what about the zeros of this function? Well, the zeros of this function are going to be given by wherever the numerator, so 2x plus 1, is equal to 0. So we just have to solve 2x plus 1 equal to 0. So that gives us that x is equal to negative 1/2. And so that's the only 0. X is equal to negative 1/2. Now, what about the wholes? So for the wholes, we need to figure out where we have a factor that cancels on both the top and bottom when this is completely factored. Now, I'm going to rewrite our function over here. We've already factored the bottom when we were trying to find the domain, and that gave us x minus 5, x plus 2, and then the top is already factored as 2x plus 1. So the wholes, we're trying to find common factors on top and bottom that would cancel, and we don't have anything that's going to cancel here. So there are none. So no wholes. I can't spell, but that's why I teach math. So we have no wholes because nothing cancels. Now what about vertical asymptotes? Now vertical asymptotes are going to be found by where, so you know how in our domain that we couldn't have negative 2 or positive 5? Well, what's happening at those value or those x values that we can't have part of our domain? And it turns out that anytime we have points that are excluded from our domain, it's either a whole or a vertical asymptote. Well, we didn't have any wholes, and so vertical asymptotes, that leaves that. But how we can tell that if we didn't even solve for our wholes yet was after we cancel everything for our wholes, we look at what we have remaining. And this tells us that x equals 5 and x equals negative 2 is where we have our vertical asymptotes. So x is equal to 5, not or. X is equal to 5 and x is equal to negative 2. is our vertical asymptotes. Now, what about our y-intercept? So our y-intercept, all we need to do is plug in 0 into our function. So if we do f of 0, that's going to give us 2 times 0 plus 1 divided by 0 minus 5, 0 plus 2, and that's going to go away. That's going to be negative 5. That's going to be positive 2. And so what we're going to see is this is going to be 1 over negative 10. And that is our y-intercept. What we could also do is we could just plug in 0 into the original function, and we would see that all of these terms would go away, and we would have 1 over negative 10 as well. But basically, y equals negative 1 over 10 is our y-intercept. And now, you won't have a question like this on your final exam with filling in tables like this. However, we will do the end behavior of a rational function. However, because I would like to make this an exhaustive review, I will do the table portion of this as well. So for this, we're going to go into our calculator and we're going to type in our function. So if your calculator is capable of making a little fraction bar like that, I recommend doing that because it makes it nicer when you're trying to type everything in. But typing in our function, we have this. And now we want to go to second table set and make sure the independent is set to ask. Because when we do that, we do second and graph, now it's not going to autofill our x and y values. What we're going to have to do is plug in these values manually. So we have negative 10,000 for our x value, and for our y value, we get negative 2. And what that e to the e negative 4 means is times 10 to the negative 4. And if you're familiar with scientific notation, that's negative 2 divided by 10,000. So it's a very small number, very close to 0. Now what if we do negative 1,000? Negative 1,000 is still a very small number, negative 0.002. What if we do negative 100? We get negative 0.19. And if we do 100, if we do 1,000, and if we do 10,000, we get similar values, just positive. So for 100, we have 0.0207. For 1,000, we have 0.002. And then we have 2e negative 4. And so again, 2e negative 4, this is equal to 2 divided by 10, but with a 1 followed by 4 zeros. So 2 divided by 10,000. Oh, and I realize you can't see that. 2 divided by 10,000. So this is a very, very, very small number. And so just from that, we can tell that the end behavior, well, as we go to negative 10,000 for x, f of x, the y value, goes towards 0. And the same happens over here. And we can deduce that, well, according to the end behavior, the limit of f of x as x goes to negative infinity is equal to 0. And the limit of f of x as x goes towards positive infinity is also equal to 0. And so if we know that this is true, that means that we can deduce that for our horizontal asymptote, that our horizontal asymptote is y equals 0. Now, if we remember back from, I can't remember exactly which section, but basically we can also look at how the degree of a rational function determines our horizontal asymptotes. So if we evaluate the degrees here, we have a couple of different things. So we have a horizontal asymptote in three separate cases. Sorry, we have three separate cases to determine like what's going on with the end behavior of our function. Two of them end up with a horizontal asymptote. So if the degree of the top is bigger, then there is none. If the degrees are equal, then it's the leading coefficient divided by the leading coefficient. And if the degree of the bottom is bigger, then it's y is equal to 0. And so if we look at our original function, we see that the degree of the bottom polynomial is bigger, and so we have y is equal to 0. I highly recommend memorizing this because it will definitely be useful on the final exam. Now, what about this problem here? So we want to see what's happening with our function as we approach -2. So as we discussed, -2 is a vertical asymptote. So we already know that much. However, how do we know that numerically? So that's where we go back to our graphing calculators. And since we're still working with the same function, I have the same values in there. But what I'm going to do to clear this out is delete, 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 delete. And instead, I'm going to type in these other values. So starting from the left, I have -2.1. Then I have -2.01. Then I have -2.001. -2. Oop. -2. Okay, there we go. I don't know what I typed. -1.999. -1.99. And then -1.9. So let's see what our function is doing as our function gets as x gets very near -2. So you can pause and just write down these values, but we can see that the values we have for -2.1, we have -4.507, then we get -43.08, then we get -428.8, we get an error, and then we have -1, sorry, looking at the wrong column. Then we have 428.35. We have 42.632, and then we have 4.058. So with this information, we can kind of figure out what's going on. So when it says error, maybe I shouldn't write error per se, but our function is undefined at this x value. And so what when it means when it's undefined is that our function, we put in an x value and then we get out usually dividing by 0 or something like that. And in this case, it is dividing by 0 because if we put in -2 into our function, we saw that, well, our function can't be equal to -2 because it's not part of our domain. The reason being is that we would divide by 0. So that's why our calculator gives us an error, is because we really cannot put in -2 into our function because it won't give us a value. So let's see what our function is doing as we approach from the left side. So remember that if you have that little negative, it looks like in the spot where there would be an exponent. If you see a negative, that means approaching from the left. And so as we approach from the left, notice the numbers are getting increasingly bigger. We start with about negative 4.5, and then about negative 43, and about negative 430. And you can imagine if we keep on getting smaller and smaller away from negative 2, this number is going to keep getting bigger and bigger. So we're going to say that this approaches negative infinity. Well, what about from the right-hand side? So again, that's approaching from the right because we see this little plus here. And we have about 4, and then about 43, and about 428. And these numbers are getting bigger and bigger and bigger. And so what we see is that this is approaching positive infinity as this number gets closer and closer to negative 2. And so that is that. So now we want to find the third term when 2x minus 3 to the power of 6 is expanded. So the first thing we need is Pascal's triangle. You will need to know this on your exam. So first we need to make Pascal's triangle. And again, I will not provide this to you. So Pascal's triangle, we start with 1, 1, and 1. And then 1, 2, 1. And how you make the triangle is that every number below on the next tier is determined by the two numbers that are directly above it. And you always have 1s on the outside. So 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And let's see, how many tiers do we need? Well, this is tier 0. This is tier 1. Tier 2, 3, 4, 5. And we need tier 6 because we're raising to the power of 6. So this is going to be 1, 6, 15, 20, 15, 6, and 1. So that's tier 6 there. And so we want to find the third term when this is expanded. And so the third term is going to be 1, 2, 3. So we want 15 here. That's going to be our coefficient of our term. So for the third term, we're going to have 15, and then we look at what we have here. This is going to be, remember, all of these are in the form of a plus b to the power of n. So if we know that n in this case is 6, we just need to identify what a and b are. Well, a in this case is 2x, and then b is negative 3. And now the last question is, what do we have for our exponents here? Well, remember, a here starts with an exponent of 6, and then 5, and then 4. So a will have, or I guess 2x in this case, will have a power of 4. And then b starts with 0, 1, and 2. So negative 3 will have an exponent of 2. And notice that 4 and 2 add up to 6. So if your two exponents don't add up to whatever n is, you know that you've done something incorrect here. But now, all we have to do is calculate this out. We have 15, and then 2x to the power of 4. 2 to the power of 4 is going to be 16. And then we have x to the power of 4. And then we have negative 3 squared. It's going to be 9. And the only thing we need to do now is just calculate what is 15 times 16 times 9. My brain's not big enough for that. So putting into our calculator, that comes out to 2,160, and then times x to the 4th. And so that is the third term when this is expanded. All right. Now, what about this? So let's find the domain of this function. So the domain of this function is, again, where this bottom here, we got to figure out where this can't be equal to 0. Everything else is going to be fine. We can plug in any number we want, but we can't divide by 0, so let's figure out where that can't be equal to 0. Well, all we have to do here is factor the bottom. That's going to give us x times x minus 2 can't be equal to 0, which means that x can't be equal to 0, or x can't be equal to positive 2. And so, since x can't be either of those values, our domain is going to be from negative infinity to 0, union, from 0 to 2, union, 2 to positive infinity. Now, what about holes? Well, look, if we've already factored this here, look at our common factors up here. We have an x minus 2 up here, and we have an x minus 2 down here. So since we have a common factor, we know that since those factors would cancel out, we have a hole at x is equal to 2. So we have a hole at x equals 2, and because we have no other common factors between the top and bottom, then that's it. Just have a hole there. Now what about zeros? Well, our zeros would be where the top is equal to 0, but notice that x minus 2 is already a hole. So we have to exclude that from being one of our zeros. That leaves just x plus 4 as a 0. So that means that x is equal to negative 4, and that is our only 0 here. And lastly, what about vertical asymptotes? So remember, when we factored out the bottom here, we still had an x. And anything that's left over in the bottom that did not factor out, wherever that's equal to 0 is going to be our vertical asymptotes. So x equals 0 here is a vertical asymptote. So there we go. All right. So let's see. Number 6. Same thing, we're going to try to find the domain of this function first. We need to factor this. Now, the top here, you definitely need to know the difference of squares formula. It will come up on your exam. I won't tell you when, but it'll come up. And basically, we need to recognize that, well, if we have something in the form of a squared minus b squared, this is equal to a minus b times a plus b. And so what we get out of the numerator here is that this is equal to, I'll write it down here, t minus 3 times t plus 3, all divided by t plus 3. So usually helpful to have these in factored form already. But now for our domain, just like last time, we want to figure out where the bottom can't be equal to 0. And in this case, we can see that, well, if t is equal to negative 3, then that will make the bottom 0. So since this can't be equal to 0, t can't be equal to negative 3, and that means that our domain is from negative infinity to negative 3, union from negative 3 to positive infinity. Now what about holes? Holes, remember, those are going to be determined by our common factors. The t plus 3's would cancel, and so our hole is wherever t plus 3 would be equal to 0, which we've already solved. We would have a hole at t is equal to negative 3. Now what about zeros? Zeros are where the top is equal to 0. Well, since we only have t minus 3 as our leftover factor, t minus 3 equal to 0, that gives us t is equal to 3. So t equals 3 is a 0 of this function. And now what about vertical asymptotes? Well, for vertical asymptotes, we don't have any other factors left over in the bottom. So there are none. All right. Now what about number 7? So I'm going to find that same stuff that we're trying to find here. First, let's just factor this. I'm going to write it up here. Okay, So factoring the top, x squared minus x minus 20, we got to find two numbers that multiply to negative 20 and add up to negative 1. That's going to be x minus 5 times x plus 4, and then divided by 2x minus 8. Notice that I have a factor of 2 in both of those, so I'm going to factor out 2. And then that leaves me with x minus 4. So now this is completely factored. Alright, so with the domain, remember our domain, we just got to figure out where this can't be equal to 0. And we see that x cannot be equal to positive 4. So for our domain, we have from negative infinity to to positive 4. Union 4 to positive infinity. For our holes, we got to find all of the common factors. We don't have any. We have x minus 5, x plus 4, x minus 4. Even though these are both 4s, the signs have to match exactly. So there are none. Now what about zeros? So zeros, we didn't have anything cancel, so we're just going to find everything where the top is equal to 0. That gives us x is equal to 5, or x is equal to negative 4. And those are our two zeros. So x is equal to 5, or x is equal to negative 4. And for the vertical asymptotes, we didn't have any terms that canceled, or any factors that canceled. So all we have to do is now find whatever leftover factors we have in the bottom, which was everything, and find out where that can't be equal to 0. And we already did that when we were finding our domain. So our domain does not include 4 because 4 is a vertical asymptote. So x equals 4 is our vertical asymptote. All right. Now moving on to 8 through 10. So identifying horizontal asymptotes or slant asymptotes. So how we do that is we have to evaluate the degrees. If the degree of the top, so I guess piggybacking off of what I mentioned earlier about the horizontal asymptotes, we have, I just threw my pen. We have a slant asymptote. Ow! I had a cat just jump on me. What the hell? And cat. Okay, that's fine. Okay. So slant asymptotes happen when degree of top polynomial is 1 plus the degree of the bottom. So look at the degree of this polynomial here. This is degree 4, but this is degree 3. So since 4 is exactly 1 greater than 3, this has a slant asymptote. But look at the degrees of these polynomials. This is 4 and this is 5. Remember when the degree on the on the bottom is bigger, then this has a horizontal asymptote. And then when the degrees are equal to one another, it is still a horizontal asymptote. All right. So now let's move on to number 11. So how do we find the equation of a slant asymptote? So slant asymptote, all we have to do is polynomial long division. So in order to set this up, we're going to have, write it over here. So we're trying to figure out how many times does 2x squared plus 3x, how many times does that go in to 4x cubed? Notice we're missing a squared term. So we have to put plus 0 x squared as a placeholder. Then we have minus 5x, and then we have plus 3. All right, so all we need to figure this out is we just need to look at the leading terms. So we ask ourselves, 2x squared times what gives us 4x cubed? Well, 2 times 2 is 4, and x squared times x is x cubed, so this is going to be 2x. And now, we multiply all of this right here by 2x. And when we do that, we have 4x cubed, and then 3x times 2x is going to be 6x squared. So if you're doing this correctly, these terms will always cancel because our next step is to do subtraction. So when we have 4x cubed minus 4x cubed, that goes away. But now we have 0x squared. This minus out here is really going to make this minus 6x squared. So 0 minus 6 is going to be negative 6x squared. Now all we have to do is bring down minus 5x, and then let's see. Okay, yeah, so bring down the minus 5x. Now we just repeat the process. We ask ourselves, how many times does 2x squared, or sorry, let me rephrase that. 2x squared times what gives us negative 6x squared? Well, we already have an x squared for both of these terms, so really all we need to do is multiply this by negative 3 to get 2 to negative 6. So if we multiply by negative 3, we get negative 6x squared, and then minus 9x. And we can do our subtraction and finish out our long division. Really, we already have our answer here, but you're going to have to know how to do long division anyway, so I might as well just finish it out. But I guess your answer here would be that the slant asymptote is y is equal to 2x minus 3. So it's this part right here. And you know you're done because a slant asymptote is by definition just a slanted line. This is a linear function in the form of mx plus b. So since you already have this part, 2x minus 3, that's your slant asymptote. But finishing out the long division real quick, minus 5x plus 9x, it's going to be plus 4x, bring down the 3, and then that would be your remainder. So all of this is equal to 2x minus 3, and then plus 4x plus 3 divided by 2x squared plus 3x. So this, if you were just carrying out the long division, this would be your answer, but your slant asymptote is going to be this part. All right, let's look at the next page. So for the following, okay, so let's find the domain of this. First, we got to factor the bottom and figure out where that can't be equal to 0. I'm just going to factor everything real quick. Well, I guess that is only the bottom because the top is already factored. So we have 2x times x minus 5. And then we got to find two numbers that multiply negative 15, add up to negative 2. Those numbers are going to be negative 5 and positive 3. So for the domain, we got to figure out where is this not equal to 0, or it can't be equal to 0. X can't be equal to 5, and x can't be equal to negative 3. And so, ordering those on your number line correctly, you would have the negative 3 first and then the 5. And your domain would be from negative infinity to negative 3 union -3 to 5, union 5 to positive. Okay, so next we have to find the zeros of the function. However, before we can determine what the zeros are, we need to know where the holes are so that we know if anything is going to cancel out. So if we look at where the holes are, we got to find the common factors. X minus 5 would cancel out, so we have a hole at x equals positive 5. So where x minus 5 is equal to 0. And now that we've done that, we can figure out where the zeros are. So because x minus 5 canceled, the only place that we can have x is equal to 0 is, or where f of x is equal to 0 is where x is equal to 0. Because 2x equals 0 means that x equals 0. So x equals 0 is our only 0, because the other one, the x minus 5, canceled because it's a hole. Now, the vertical asymptotes, whatever factors we have left over in the denominator are going to be our vertical asymptotes. So x plus 3 equals 0 means that x equals -3 is a vertical asymptote. Now, what about the horizontal asymptote? Well, two ways you can do this. You can multiply the numerator back together because the denominator is already multiplied together in the initial problem. Or you can recognize that, well, I have 2x times x here, and that's going to give me a 2x squared. And well, I don't even care about the other stuff. We don't even need this -5 because when we're trying to figure out the horizontal asymptote, all we need to do is evaluate what is the degree of the top and what is the degree of the bottom. So for the horizontal asymptote, if the degrees are equal, it's going to be the leading coefficient divided by the leading coefficient for both of those polynomials, where the leading coefficient for the top is 2, and the leading coefficient of the bottom is 1. So your horizontal asymptote is 2 over 1, which is 2. And lastly, for your y-intercept, we just have to plug in 0 into our function. So if I do multiply all of this out, it's usually the easiest when it's all multiplied out, but 2x squared minus 10x. Now notice if I plug in 0, because remember the y-intercept is where what the y value is when we plug in 0 for x. If I plug in 0 here, this is going to go away, that's going to go away, and I'm basically going to have 0 divided by -15, which is equal to 0. So that is that. Okay, and now we have some transformations. Sorry, not transformations, I'm looking at a different page. That's the next page. But we want to use this function to answer the following. So the domain. So I'm going to use a different colored pen just so it doesn't look like red, at least on the graph, because we have red on red. And notice that this function Okay, that one's kind of hard to tell. I'm assuming the vertical asymptote. Okay, yeah, the vertical asymptote looks right. Okay, so vertical asymptote there. And it looks like we have a hole right here. But for the domain, our domain is going to be all of our x values, or it's going to be all of our x values that are valid. So basically, we got to figure out where is our function not have a valid domain for. And the x values that can't be part of our domain are -2 and +2. So our domain is going to be from -infinity to -2, union -2 to 2, union 2 to +infinity. So everything else is fine, but we don't have our domain defined for -2 and 2 because we have a vertical asymptote hole there. Now, what about the zeros? Well, the zeros are going to be anywhere that our graph touches the x-axis, right? So just approximating this, I'm going to say this is x is equal to negative 1 point, negative 1 point, I don't know, 7. And that is our 0. Now, what about the y-intercept? Y-intercept is where our function touches the y-axis. That is going to be right there. So our y-intercept is where y is equal to negative 2. Now the limit notation on the whole. So what we're trying to see is what is happening with our function as x approaches 2 from the left and from the right. As I just switched, so from the left and the right. So from the left, as x approaches, not from negative infinity, as x approaches 2 from the left, and then the limit of f of x as x approaches 2 from the right. That's what we're trying to figure out here. So as our function approaches 2 from the left, what's the y value approaching? Okay, well the y value approaches 1, 2, 3. And as our function approaches from the right, as we get right up to the hole, the y value is also 3. So that is our limit notation for the hole. Now what about the end behavior? What is our function doing? So limit of f of x as x approaches negative infinity, and limit of f of x as x approaches positive infinity. So what's happening here? Well, look at our graph. As our x value goes way out here towards towards negative infinity, what is the y value doing? It's going down, really far down. And so this is equal to negative infinity. Now, what is our function doing as our x value gets really big and goes towards positive infinity? Well, our y value is going up. And it just keeps going up. It's never going to stop. So that's equal to positive infinity. Now, what about the limit notation on our vertical asymptote? So we only have one vertical asymptote here. And so again, we're going to figure out, well, what is it doing? What is the limit of our function as x approaches, let's see, that's going to be negative 2 from the left, and the limit of f of x as x approaches negative 2 from the right. So what's happening? Well, let's see, as we approach from the left, so as x gets really close to the vertical asymptote from the left, look at what our y value is doing. It's going really far down. So this is going to be negative infinity. And now, what is happening with our y value as x approaches from the right? Well, our y value starts to go up really, really far, up towards positive infinity. And now, I want to circle the statement that describes the graph. Has a horizontal asymptote? No. Has a slant asymptote? Maybe. Does not have a horizontal or slant asymptote. Okay. Well, our slant asymptote can be given right here. Notice that if I were to draw a dotted line, and I'm going to do my best here, but notice that our graph is following along a slanted line like this. That is our slant asymptote. So there we go. The graph of f has a slant asymptote. Now, what about transformations? So transformations on these functions, we're going to do these graphically first. So we got to remember, what are these transformations doing? So minus 3 inside of our parentheses here is going to be right 3. And plus 4 on the outside of our parentheses here is going to be up 4. So let's just move this function right 3. Let's see, and then up 4. So all of our points are going to go right 3 and up 4. So I'm going to look at this point right here, 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 and here. So these 5 points are probably really good points to look at. So if we do right 3 and up 4, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4. And there we go. So now I've moved all of these points, right 3, up 4, and if I connect them the way that they're shown in this graph here, it's going to look like that. And so that is our visual graphical transformations here. Okay, what are the transformations that are done here? So that minus there, that's going to be a vertical reflection. So our graph is going to get flipped upside down over the x-axis. What is this 2 here going to be? That's going to be a horizontal dilation by 1 over 2. And so what does a horizontal dilation mean again? That means that our x coordinates are all going to be multiplied by 1/2. So what that's going to do is that's going to squish everything towards the y-axis. And then this last transformation here is just going to be up to 5. So we got a lot going on here. So first what I'm going to do is I'm going to do the vertical reflection and the horizontal dilation, and then I'll move the whole thing up 5. So the vertical reflection first is going to move everything like this. So this point is going to go up here. This point is going to go all the way down here. This point is going to go right there. This point right there, and then right there for that point. So that's the vertical reflection. And now the horizontal dilation is going to, again, multiply all of the x coordinates by 1/2. So this point now is going to move over here. This point right there. This point right there. And I'm going to erase the old points as I do these because this is going to get really confusing really quickly. This point is going to be, so if this is at 3, this is going to be 1.5. And this point at 4 is going to be 2. So now we've done the horizontal dilation. And the last part is moving all of this up to 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then also right next to it. So now I can erase the old points, and we have our graph. So let me just connect those. We have this, and then it does a little shape like that, and it connects like that. So notice that, again, this function here just got squished inwards, and so that's why this bowl shape here, one, it's upside down, but it's also narrower than it was initially. But that's our graphical transformations. Last part here, this 3 is going to be a vertical dilation by 3. And then we have, this is going to move right 1 again. So we do the vertical dilation first. So vertical dilation by 3 is going to stretch all of our y-coordinates. It's going to multiply all of our y-coordinates by 3. So if this is 2 right here, this is now going to go all the way down here. This point is 1. It's going to go all the way to -3. -2 is going to go all the way to -6. And then +1 is going to go up to +3. And +1 also to +3. So our graph now looks like that. And now we just have to move all of this right 1. So if I move this right 1, that's going to go over there. Erase the old point. This one's going to go over here. Erase the old point. This one is going to go over here. Erase the old point. This one's going to go over here. Erase the old point. And this one's going to go over here. Erase the old point. And so now we just have to connect this, and we get a shape that looks like that. That's definitely a straight line. But that is what our graph should now look like. All right, now let's do these algebraically. So we want to figure out what these functions are going to look like once we transform them with our rule for g of x. So for number 17, we see that g of x is given by f of x plus 2. So all that means is that where we see an x in f of x, we're going to replace it with x plus 2. So this x squared becomes x plus 2 squared. Then we have plus 3 times x plus 2, and then minus 5. So x squared becomes x plus 2 squared. 3 times x becomes 3 times x plus 2, and then we still have the minus 5. And all we have to do now is just simplify this. So x plus 2 squared is going to be x squared plus 4x plus 4, and then plus 3x plus 6, and then minus 5. Combining our like terms, we have x squared, 4x plus 3x is going to be plus 7x, and then 4 plus 6 minus 5 is going to be plus 5. And so that is our new function g of x. Now what about number 18? In g of x, we want to replace f of x with 2x squared plus 4x. So fortunately, that's a pretty straightforward substitution, because all we have to do is write now 1/2 times all of this, which is f of x. So we have 2x squared plus 4x, and then minus 5. So 1/2 times 2 is the same thing as 2 divided by 2, which is just 1. So this is going to become just x squared. And then 1/2 times 4 is the same thing as 4 divided by 2, which is just 2. So plus 2x, and then minus 5. And that is it. Lastly, for number 19, we have negative f of 3x plus 4. So my recommendation for this is first just figure out what f of 3x is, because if you try to plug all of this in, it can get a little bit confusing. But f of 3x, now every time we see an x, we're going to replace it with a 3x. So f of 3x is 3 times 3x plus 1. And that gives us 9x plus 1. And so now that we know that f of 3x is 9x plus 1, we can substitute that in here. That means that g of x is equal to negative f of 3x, which we've already determined is 9x plus 1, and then plus 4. So now distributing this negative, we have negative 9x minus 1 plus 4, and combining like terms, we have negative 9x plus 3. And there we go. So that is our new function g of x. And the last stuff we have for this review is just figuring out the let's see, what is it? Hold on, I feel like there was another page here somewhere. Oh, there was. Okay. So these are not the last two problems. All right, so given this table of values, we want to figure out what g of 1 is given this function. Okay, so g of 1 is going to be the same thing as f of negative 2 times 1 plus 2. I highly recommend knowing how to do this type of problem because this was very missed on our last exam. So please understand how to do this and follow along. But negative 2 times 1 is just negative 2. And then we have plus 2. And now that we know we have to figure out f of negative 2, that's when we look at our chart here. So what is f of negative 2? F of negative 2 is when x is equal to negative 2, f of x is equal to 12. So this is equal to 12 plus 2, which is 14. And that's all we have to do. I saw some pretty crazy answers on our last exam. And the same thing over here. What if we're trying to figure out g of 1? Okay, well, g of 1, all we have to do is replace this x with 1, simplify, see what we get. So this gives us negative 2 times f of 1 minus 1 minus 3. That means we have negative 2 times f of 1 minus 1, which is 0, minus 3. Now we have to figure out what f of 0 is. Well, f of 0 means that when x is equal to 0, f of x is also equal to 12. So f of 0 is equal to 12. So since we know that f of 0 is equal to 12, we have negative 2 times 12 minus 3, which means we have negative 24 minus 3, which is negative 27. And so that is our final answer. The last part of this is figuring out domain and range of these functions. So let's see what's happening here. So for the domain of f, we have negative 1 to 3, but not including negative 1 and 3. For the range, we have from negative 5 to 10. And now we need to understand how these transformations affect our domain and range. So starting with our domain, this plus 1, what does that mean? Plus 1 means that we are moving left 1. So that's going to affect our domain. So that means that our new domain, we're going to have to, if we're moving to the left 1, we're going to have to subtract 1 from all of our domain values. And so that's going to give us -2, 2. Now what about our range? The only thing affecting our range is this vertical dilation by 4. So again, vertical dilation by 4. Remember, that's going to stretch all of our y values away from the x-axis. All of our y values are being multiplied by 4. And so what we get here is -5 times 4, which is -20, and then 10 times 4, which is 40. And so that is our new domain and range for this function. And lastly, for number 23, the graph for f has a domain of -10 to 4, so I'm going to write that down. So domain -10 to 4, and our range from -3 to 6. So what's happening here? So, okay, we have a lot going on. This 2 right here is going to be a horizontal dilation by 1/2. We know it's a horizontal dilation because if it was a vertical dilation, it would be on the outside in front of the f. But since it is inside the parentheses multiplied by x, it's going to be a horizontal dilation. The -2 is going to be right 2. And the +4 is going to be up 4. So let's look at the ones that affect our domain. That's going to be the horizontal dilation and being moved right 2. Everything on the inside of the parentheses of f of whatever. So first we do the horizontal dilation, and then we'll move everything right. So if we do the horizontal dilation, all of the x values get multiplied by 1/2. That means that we now get -5, 2, because all of this gets multiplied by 1/2. And then moving it right 2, since we're moving that way, everything's going to have 2 added to it. So that's going to give us -3, 4. And this is our new domain. Our new range, all we have to do is go up 4. And so adding 4 to everything, -3 is going to become 1, 6 is going to become 10. And this is our new range. And so that is how we do the entire Unit 1B corrective assignment. So yeah, thank you for watching.